Hello everyone, this is Roushan and today I will be going to conduct live session which is based on week 11. In the previous session, I have conducted the session for week 10 in which we study about bending of beams and shear center, and several numerical example I have solved there. I think you have understood the concept there. And if you have any doubt, please ask me here. Today I will be going to discuss energy methods, which is covered under week 11. Okay, so let's start today's session. So week 11, in week 11 we have two lectures, lecture 29 and lecture 30, which is based on energy methods. So week 11, it has two lectures, which is based on energy methods. Okay. So in the previous lecture, I told you that we can find the deflection and the slope of a beam, of a deformable beam through various methods, through equilibrium equations. Okay. So this is alternate approach where we can use the energy of the system. Through energy of the system, we can find out the deflection as well as slope of the system after having application of some external forces or moments. So energy method is one of the method through which we can find the deflection and slope of the beam. So in this session, I will solve some problem related to this concept. So here there is a concept that is called influence coefficient. So it is just like the stiffness of the spring mass system. So it basically depends on the location of applied forces and the point where displacement is being measured. So it depends basically on two things. The first that is the location where the forces is applied, and the second is the point where the displacement is from where the displacement is measured. So using this, we will solve some problem later on. So it has one relation, that is the reciprocal relation. Okay, so through which we can find out the energy of the system. So that is reciprocal relation. Reciprocal relation. So it allows, basically reciprocal relation, it allows us to obtain relationship between influence coefficient, that is Kij and Kji. Kij and Kji. Okay. And using this, we can find out the using the influence coefficient, the concept of influence coefficient, we can find out the energy. So energy stored in a body, energy stored in a body will be E equal to half F1 delta 1, or we can say half K11 F1 square. So this is basically influence coefficient. Okay. And this is the deflection, or we say displacement. The next thing that will be discussed in that lecture is the Maxwell-Beatty-Rayleigh reciprocal theorem. So one theorem is there, that is Maxwell-Beatty-Rayleigh reciprocal theorem. Okay, so this theorem states that work done by forces, so I basically write the simple formula, that is summation of all the forces acting on a body times displacement is equal to summation of all the forces time displacement. It means that, so here I wrote two different type of forces, Fi and Fi dash, and in the same way I wrote two displacement, that is delta I dash and delta I. So it means that work done by forces in situation 1 through the corresponding displacement of situation 2 equals the work done by force in situation 2 through the corresponding displacement is. So it means that work done by forces work done by forces in situation 1 through the corresponding through the corresponding through the corresponding displacements through the corresponding displacements of situation 2 equals the work done by forces in situation 2 through the corresponding displacement in situation 1 through the corresponding displacements in situation 1. Okay, so this is all about Maxwell-Beatty-Rayleigh reciprocal theorem. I will be using this concept in solving while solving the numerical problems. The next thing that is discussed already in the lecture there, which is the Castigliano theorem. So basically we have two theorem based on given by Castigliano, that is Castigliano first theorem and Castigliano second theorem. Okay, so using the Castigliano theorem, we find the energy due to bending, energy due to twisting, energy due to shearing, energy due to extension. So using Castigliano theorem, we can find the energy of a beam under several loading condition. So I just simply write the formula for the uh, energy for different kind of deformation, that is in the case of extension, in the case of stretching, shearing and twisting and bending, of course. So I simply write the energy due to bending. First I will write the energy due to stretching. So this is the formula for energy due to stretching, where P is the applied load, A is the area of the cross section, and Y is the Young's modulus. This is area, sorry. So this is area of the cross section, area of the cross section, sorry, Young's modulus. This is basically Young's modulus, sorry. This is Young's modulus. This is area of the cross section. And this is the load applied, okay, external load applied. Similarly, energy due to bending. Energy due to bending. So it is given by mz square upon 2e izz. So this is the relation for energy due to bending. Next is energy due to twisting. Energy due to twisting. Energy due to twisting. So it is given by this relation. T square upon 2gj. Next is given by energy due to shearing. Energy due to shearing. It is given by this relation. V square upon 2 times kappa Ga, where K is the kappa is the shear correction factor. That means the total energy stored in the beam in general case can be written as, so total energy stored in the beam in the general case is given by E equal to integral over 0 to L, because all the energies that I written above is the energy of a cross section. So basically we have to integrate the energy of the cross section over the length of the beam, so that we can get the entire energy stored in the beam due to all kind of deformation, that is extension, shearing, twisting and bending. So it is given by simply px square upon 2ea plus my x square upon 2eizz plus mz x square upon 2eizz plus tx square upon 2gj plus vy x square upon 2 times kappa Ga plus vz x square upon 2 times kappa Ga whole square times dx. So it is the total energy stored in the beam. So we will going to use this equation most of the time, because the numerical that I will solve today is basically based on the energy method, and all the numerical that I solved today is to find the deflection and the slope of or the reaction force, something else. So all the problem were basically based on the energy method. You can solve it via equilibrium equation also, that I earlier discussed in the previous week. But today only you can use any method. You can use energy method, you can use equilibrium equation method using the force equilibrium equation. So you can use any method to find out the deflection and slope of the beam. But today I will going to use only energy method to solve any kind of problem. Okay. So this is the final equation that we have. So this is all about the lecture. So the complete derivation of this equation is already given, is already taught in the lecture. So if you want to know how it derived, so please, I request you to please go through the lecture carefully. And I surely, I assume that you already done the lecture before coming to the session. So now I will solve, I will going to start the problem solving session. So let's start the problem solving session now, which is the main aim of this session. So I just briefly recapitulate the things, that so that you can recapture all the theory part, so that it will be easier for to you to understand here the numerical problem easily. Otherwise it will be difficult to understand all the concepts, because I'm going to apply all the concepts which is already covered in those lectures. So let's start. So the first problem is question number 1. Problem 1. So this question says, think of a rectangular beam as shown below. So here we also have a figure as shown below. Assume its cross section to be solid, circular. Suppose the ring is subjected to is subjected to equal and opposite forces at A and B. Neglect energy in the beam's cross section due to shear force and axial force. So here we have the figure. Yeah. So here a force is applied. So we have 4 points. That point is D, A, B, C, and a load is applied P here, and from the upside also P here. This is of height H, and this is of length L. The radius of the beam is 2r. So based on this statement, we have a question here. So the question is, the first part of this question is, by how much by how much will points A and B get closer to each other? The second part of this question is, by how much will points C and D get farther apart? C and D get farther apart. And the third part of this question is, what is internal moment? What is internal moment in the cross section at C? In the cross section at C. So here we have a question. I'm repeating the question. Think of a rectangular beam as shown below. So we have a rectangular beam here. Assume its cross section to be solid circular. So the cross section of this beam is circular. Actually, circular beam is there. So the cross section of the beam is circular, solid circular. Next is, suppose the ring is subjected to equal and opposite force at A and B. So you can see in the figure that we have two equal and opposite force acting from upward and the downward side. That is a force P. So neglect energy in the beam's section due to shear force and the axial force. So here we are assuming that there is no shear force and axial force uh, in the beam. So this is an assumption. So based on these statement, we have three questions. So the first part of this question is, by how much will point A and B get closer to each other? And the second part of this question is, by how much will point C and D get farther apart? What is the internal moment in the cross section at C? So suppose we have basically a square type beam, and we are pressing from both sides. So what happened actually? So the adjacent, that is the opposite sides, these two sides will get apart, and the upper two sides will get compressed. So the final figure just after the deformation will be, so the solution part now. So the final figure, I am drawing the final figure just after the deformation happened. So suppose this is a square beam, rectangular beam, sorry. Yeah. So we have this rectangular beam, and after deformation and a load is applied from above and from below. Okay, just after the deformation, it will be like this. Okay, so just after the deformation, it will be like this. So, and this is the point, the 4 points here. This point, sorry, this point A, then B, this is point C, and this is point D. Okay. So the first part of this question is, how much will point A and B get closer? So A and B get closer by some amount. Actually, you can see in the figure also, after deformation, it will look like this. And you can see here that it get deformed. So some displacement happened here. And similarly, for the point C and D, it gets farther. So some displacement also happen here. So we have to find that distance actually. So first write actually. So let's break this part in two sections. So we can always do that. We can always do this to draw the free body diagram of the system. So let's bifurcate it in two parts to analyze the internal forces which is acting in the system. So okay, so this is our upper part, this point A, and here a load P is applied from the topward. So because these 2 points, you can see here, these 2 points, to remain in equilibrium, actually it exerts some reaction forces which is acting upward. So because the external force is acting downward, so to maintain equilibrium, equal and opposite, because it is acting at a same at a, because this length is what, this length is L by 2, this length is L by 2, yes. So this is the force P is acting at equal distance from both the ends. So that's why the, to maintain equilibrium, equal and equal forces acting at two ends, that is Fc, which is at point C, which is equal to P by 2. Here also Fc is acting, which is equal to P by 2. So this is the part. Now we can always do that. We are supposing that this point that is A point is rigid, and we are always work with 1/4 of the ring. So here I bifurcate the ring into two parts, and I just write the internal forces and external forces acting on the upper part. We can also break it in one more part, that is 1/4 of the ring, and using this we can basically analyze the forces acting in the system. So let's do that. So this is point A, and this is 1/4 of the ring, and this is point C. And you see from the figure that will become, that the half figure will become this way. Okay, so we draw the FBD for the system. So here we are assuming on shear force is acting, that is Vc, which is again 0, because in the question it is already mentioned that there is no shear force due to this deformation. There is some force acting in the upward direction, which is Fc. Here also I have mentioned that. So which is Fc equal to P by 2. So this is the free body diagram for the system. Now we always know that from the Castigliano theorem that to find out the deflection, we have to take the derivative of, to find out the deflection at any point, we have to take the derivative of energy, total energy of the system with respect to the force applied at that point. And similarly, to find out the slope of slope at any point, we basically what to do, we have to find the derivative of total energy of the system with respect to the moment at that point. So if any if no moment or force is acting at that point, so basically we what we do is we uh, we use a dummy moment or dummy force. So basically we put a dummy moment or dummy force at that point, and and we go through the process, that is the, to find the deflection, we write the energy of the system in terms of the dummy moment, or we can say force, and take the derivative of derivative with respect to the force at that point. And after taking the derivative, put the dummy moment and dummy force value to be 0. Why? Because it's a dummy moment and we forcefully apply that moment, but actually it is not existing. That's why we have to keep it 0 at the final stage. So using that concept, we are going to solve this question. So first, I will break this whole system into two parts. The first part is this one and the second part is this one. So I write the FBD for both the parts. So it can also be visualized as so this distance is h by 2, and where here we have a shear force acting Vc, which is equal to 0, and here from here we are taking some section which is at a distance x from the endpoint, that is at point C, and here we know force is acting Fc. In the lower part, a shear force is acting in the upward direction to maintain the balance, to maintain it at equilibrium. This is Vc, which is again equal to 0 at that point, and here a moment is acting, moment at C, moment at x. So at section x we have moment x, here also moment at C acting. So this is at a section S, this is at a section of x, here also moment at C is acting. There is a force Fc which is equal to P by 2. Now coming to this part, so here we are taking the reference from this position and we are taking in the section at any this point. So in this case also we have shear force Vc which is equal to 0. There is a moment acting, moment at C, and there is a force acting which is equal to Fc equal to P by 2. Now this point, so here also there is a shear force, we are assuming there is a shear force acting, and we are assuming there is a force also, there is a reaction force because it is fixed, and support. So here also a force is acting, and there is a moment also applied here, that is mx. Now coming to this point, there are also shear force is acting, which is assuming, we are assuming that shear force is absent here. Here moment about C, there is a force Fc is acting which is equal to P by 2. Okay. Now we have converted this problem in two sections. So the vertical part and the horizontal part. So we will solve this question in two way, in two process. The first I will solve the problem for vertical, then horizontal part. So let's start with the vertical part. So vertical part, in the vertical part, I basically balance the moment and forces, balance of linear moment and the balance of moment and balance of forces. So I am using the equilibrium equations here. So first start with the moment. So m is equal to mc plus this shear force also generate moment vc into x, and for the horizontal part, mx is equal to mc plus vc into h by 2, because why is it so? Because distance is h by 2, because this distance is h by 2, vc into h by 2 plus fc into x. You can see here that Fc is acting. So this is the length here, L by 2. So Fc into x, Vc into h by 2. This distance is h by 2. So the total energy due to bending will be total energy due to bending. Total energy due to bending will be, which is a function of Fc, Vc. Vc is the shear force, and mc. So first we have to integrate over 0 say h by 2, then we have to integrate over a0 to L by 2, because we have 2 bar just like L shape. So 0 to h by 2, then 0 to L by 2. So integration over 0 to h by 2 mc plus vc square. So here the moment is, sorry, so here the moment is mc plus vc into x. So mc plus vc x whole square upon 2ei into dx plus integral over 0 to L by 2 mc plus vc into h by 2 plus fc into x whole square upon 2ei. So this is the total bending energy of the system. Now here we can see that Vc equal to 0, Fc equal to P by 2, and Mc is unknown, because here Mc is unknown value. Now we are using the setting here, that is the derivative of energy with respect to moment at C will be 0. Why? Because at C you can see that there is no moment, there is no rotation happen, that is there is no slope. Actually it only translated, the point C is only translated to some other point, so there is no rotation. That's why moment about C is 0. That means del E over del MC, that is derivative of E with respect to MC, will be 0. So we are using the concept here. MC for rotation at C rotation at C will be 0. Therefore we can say that del E over del MC equal to 0. So that means 0 to h by 2 MC plus Vc into x. So del E over del MC is upon EI dx plus integral over 0 to L by 2 MC plus Vc into h by 2 plus Fc into x upon EI into dx equal to 0. Now here we are assuming a dummy shear force acting here at point C, which is now to be 0. So at the last, after taking derivative, we will have to put the value of Vc is 0. So after putting the value Vc to 0, so it will become, this get cancel out, this term cancel out, this term will also cancel out. And what is Fc? So Fc, from we find the Fc value through FBD. So Fc here is found to be P by 2. Now again, so this equation will become mc into h by 2EI plus, after integrating this term, mc into L by 2EI plus PL square upon, please tell me if I do any mistake, 16. So it will become FC is P by 2 integral over 0 to L by 2 x. So x will become x square by 2. And what is L here? L is L by 2. So it will become L by 4, that is L by 8, so 16. So PL square upon 16 EI equal to 0. So from here we can find the value of MC, which is minus PL square upon 8 L plus H. So this is the value of MC, moment at C. So what is the internal moment in the cross section at C? So we found that we solved this question. The third part of this question is asking about the internal moment in the cross section at C. So the internal moment at the cross section at C will be minus P L square upon 8 into L plus H. Now we have to find the how much point A and D and how much point A and B and C and D displays. So to solve that problem, we basically assuming. So you can see that A and B displays A and B total displays by some amount. So the displacement from here to here and from here to here will be equal. Similarly, displacement from here to here and from here to here will be equal. So we can say that the displacement of CD will be same as 2 times of displacement of C, and similarly the displacement of AB will be 2 times of displacement of A. So let's write this. Delta, that is displacement of CD, will be equal to 2 times of displacement of CX. Okay, where CX is what? So CX is horizontal displacement of point C. Delta CX is horizontal displacement of point C. And here we have a question, we have to find the value of this one, that is delta Cx is what? So we can use the Castigliano theorem to find the deflection. So that is delta Cx is given by del E, that is total energy of derivative of total energy with respect to shear force at C. And Vc is here is already 0, but we are taking the derivative with respect to Vc assuming it is present, and after taking derivative we are forcefully put the value of this equal to 0. Sorry. So let's find out the derivative with respect to Vc. So if we take the derivative of this energy with respect to Vc, we will get Vcx upon 2EI, Vcx upon EI, Vc upon EI. So after taking the derivative with respect to it becomes 0, it will also will become 0. So after putting this value, so let's do this. So this is the energy, I just copy the energy from here. So this is the energy of the system, and we have to find the del E upon del VC. So del E upon del VC, 2 times MC plus VCX upon EI integral over 0 to h by 2 into dx plus integral over derivative of VC, so into x dx plus integral over 0 to L by 2 times, so 2 to cancel out, MC plus VC into h by 2 plus FC into x into h by 2 into dx. And after taking derivative, we have to cancel out each term. So VC is going to be 0, so this term cancel out. VC is going to be 0, this will cancel out, this will become P by 2. So take the derivative with respect to this one. So MC upon EI x square by 2. So what is x square by 2? That is h by 4 h by 8. So MC h upon 8 EI. MC h square upon 8 EI plus MC h L by 2, MC h L by 4, and FC x, this is 2 EI also. So it becomes EI FC into FC is P by 2, so P by 2 L square by 4, that is L square by 8, that is L square by, so P L square upon 16 EI into H by 2 equal to 0. Okay. So 1H will cancel out from each the term. So it will become MCH upon 8 EI. EI will also cancel out. EI sorry, this is not equal to 0, so I just can't cancel it out. MC H square upon 8 EI, so we will take MC H upon 4 EI as common. This will become H by 2 plus L plus PL square H upon 32 EI. What is the MC value of MC here? We found out minus PL square upon 8 into L plus L minus PL square upon 8 into L plus H into H upon 4 EI 2h plus 2l upon 2 plus PL square h upon 32 EI. So it will become minus PL square upon EI 32 EI upon h into h plus 2l upon 2 into l plus h plus PL square upon 32 EI is common plus h. Again minus PL square upon 32 EI. This is minus h into h plus 2l, that is h square plus 2hl minus 2lh minus 2h square upon 2 into l plus h. So LH, 2LH, 2LH get cancelled out, and the remaining thing that will remain is h square upon 2 times l plus h, that is PL square h square upon 32 64 EI into L plus H delta CF. So this is the final expression for the delta Cx. Using that we can find out the value of delta Cx. Now coming to the, so we found the value of delta Cx. So delta AB is given by 2 times of delta Cx. Now we have to find the value of delta Cy. Okay, so this is what, so it is given by, because it is in the vertical direction, this is the displacement along vertical direction, so that's why we have to take the derivative with respect to vertical force, that is Vc. Sorry, vertical force is Fc, because in the previous case there is a horizontal force acting. You can see in the figure also, for the vertical displacement, for the horizontal displacement we have to equate it with the shear force Vc, so therefore we take derivative with respect to Vc. Now we have to find the vertical displacement. For that we have to take the derivative with respect to vertical force, that is Fc. So del A upon del E Fc. So what is the energy? I just copy the energy one more time. So this is the energy, and if we take the derivative with respect to Fc, we will get, this will cancel out. This will cancel out because here is no Fc. The only term that will remain is this one, 0 to L by 2. mc plus vc into h by 2 plus fc into x upon 2 ei into dx. So it will become mc into l by 2 ei, not l because x also, so x square by 2, that will become x square by 4, x square by 2, x square by 8. mc x is become l square by 16 ei plus Vc into h by 2 x square integration of x is x square by 2, then it will become x square by 4, x square by 4 by 2, that is x square by 8, 16 VCH L square upon 16 EI. Is it correct? X square by 2, 2, 2, it is 8 actually, plus FC into x square by 2. Now because here VC is 0, so basically we put VC here to be 0. Sorry, VC here to be 0. FC is into x will become plus FC into L square by 8 EI. And MC, we found the value of MC, which is minus PL square upon 8 EI. L plus 8 EI is already there, so 8 8 64 into L plus H into EI into L square, plus FC is P into L by 2. FC is what? P into, FC is P by 2 actually. So P by 2 into 8 EI. Here also there is a x, so it becomes x cube by 3, x cube by 3, 0 to L by 2, which is 8, 3 24, 24 EI cube. So it becomes P by 16 EI minus L to the power 4 upon 4 into L plus H plus L cube upon 3 into 3, just only 3. So if we take the LCM, we will get P upon 16 EI minus 3L to the power 4 plus 4L to the power 4 plus 4L cube H upon 3. So it will become P upon 16 EI L to the power 4. So if we take L common, so it becomes L 4H plus 1, sorry, 4H plus L. That's correct, I guess. Yes. Upon 3. So this is the value of delta CY. So delta AB, delta CD, that is the vertical displacement, I guess. So this is actually delta CD, horizontal displacement, and this is a vertical displacement delta AB is equals to 2 times delta CY. So this is all about question number 1. We have found the value of the displacement, horizontal displacement as well as vertical displacement. So this is all about question number 1. Now move on to the next question. It is problem number 2. So this problem states that using energy method, energy method, using energy method, determine, first is the vertical deflection, of point B under the action of load W, under the action of load W. And the second part of this question is the horizontal reaction force at B. The horizontal reaction force at B. The horizontal reaction force at B. Okay. The end B is free to rotate. The end B is free to rotate, but can move only in vertical direction. Consider all forms of energy. That is bending, twisting, stretching, as well as shearing energy. So we have a question, we have a figure also here. So I will draw the figure first. So I am repeating the question. Using energy method, determine the vertical deflection of point B. So here the point B is. So we have to find the reflection at point B, and under the action of load W. So here load W is acting downward. And the next part is the horizontal reaction force at B. So at B, we also have to find the horizontal reaction which is acting here. The end B is free to rotate, but can move only in vertical direction. So it's free to rotate, but can move only in vertical direction. So there is a horizontal constraints here. So there must be a reaction force acting in the horizontal direction. Now the next part is the end B is free. Yes. Consider all forms of energy, that is bending, twisting, stretching, as well as shearing energy. So here we have to consider all form of energy. That means here there is no assumptions made. So let's start the solution first. I copy this figure again so that I can use this figure one more time. Now suppose there is a section here at an angle theta, and we are solving the FBD for this problem. So this is a circular roller. Here there must be a horizontal reaction force. Why? Because there is a constraint. It is this figure does this point doesn't move in the horizontal direction. So there is a reaction force acting RP. There is also a moment, dummy moment. It can rotate, so that's why the moment here is to be 0, but we are applying here dummy moment to find out the deflection at point B. Now let's take a small section here, this section. Now let's take this section and draw the FBD of this section. So this is angle theta. Here there is a reaction force acting RB. Here there is also a moment about B, which is equal to 0. This is of radius A. To maintain the equilibrium, there is a force acting along theta direction, that is F theta. There is also a shear force acting V theta, and there is also a moment which is M theta. Now let's draw this FBD. So if we take this is angle theta, here somewhere here a force is acting, which is RB, reaction force. This is W, is the downward force acting. Moment here acting, which is 0. Now this angle is A, so this become A cos theta, and this is A sin theta. Here there is some forces acting, that is F theta. This is V theta, and there is a moment M theta. Now let's find out the value of F theta, V theta and M theta. The extension, that is the compressive force, shear force and the bending moment. So F theta will become RB cos theta minus W sin theta. V theta will become RB sin theta minus, this is V theta, RB sin theta. So I'm taking one, so this angle is theta, sorry, this angle is theta, so this angle is also theta. Okay, so RB cos theta, RB sin theta, RB sin theta minus, sorry, RB sin theta plus W cos theta. I guess I am right. Yes, W cos theta plus W cos theta. Similarly, M theta will become MB minus WA minus WA sin theta minus RB A into 1 minus cos theta. So the total energy in terms of FB, RB and MB is given by the total energy is given by, so here we are considering extension, shearing and bending, because this problem does not create any twisting, so that's why it is 0. Otherwise it will also come, because here there is no assumption made. So that's why here all the forces, all the energy due to stretching, bending and shearing will come. So total energy is given by in terms of RB, FB and MB is given by 0 to, so this angle is completely not 360 degree. If you see this circle, if you see this beam, this is not a complete 360 degree. This is some 180 plus 90, that is 270 degree. So that's why we have to integrate the section over 0 to 3 pi by 2. F theta square upon 2 EA plus V theta square upon 2 kappa GA plus M theta square upon 2 EI into d theta. Now we already know the value of F theta, V theta and M theta in terms of RB, FB and MB. So I just simply write here. So F theta is RB cos theta, RB cos theta minus W sin theta whole square upon 2 EA plus RB sin theta plus W cos theta upon 2 kappa GA whole square plus MB minus WA sin theta minus RBA into 1 minus cos theta whole square upon 2 EI A d theta. Now we have to find the particle deflection of point B under the rectangle of load W and the horizontal reaction force at B. So you can see here that RB, there is no horizontal displacement happen here. So that's why the derivative of energy, total energy with respect to RB is equal to 0, because there is no horizontal displacement here. There is only vertical displacement. That's why we can say that since the beam has no horizontal displacement, since the beam has no horizontal displacement, or we say horizontal deflection at point B, at point B. So we can say that del E over del RB equal to 0, and MB, that is moment about B, is also 0, because here we are using the dummy moment to find out the slope at point B. So we put it 0 after taking the derivative of energy with respect to RB. So if we take the derivative, we will get integral over 0 say 3 pi by 2, integral over 0 to 3 pi by 2, RB cos theta minus W sin theta upon EA cos theta plus RB sin theta plus W cos theta upon kappa GA into sin theta plus MB minus WA sin theta minus RB into A into 1 minus cos theta upon EI into minus of A into 1 minus cos theta into A d theta. So this is the total integration, and that must be equal to 0. Here also, because we have taken the derivative here, and WMB is the dummy moment at B, so that's why it's 0. So finally it become my A times 3 pi RB minus 2W upon 4EA plus 3 pi RB plus 2W upon 4 kappa GA plus WA square upon 2EI plus RB A square 2 plus 9 pi by 4 equal to 0. From here we will take RB as common, because we have to find the value of RB. So RB times, if we take common here, we will get 3 pi upon 4 EA plus 3 pi upon 4 kappa GA plus A square into 2 plus 9 pi by 4 equal to W times 1 by 2 EA minus 1 by 2 kappa GA minus A square upon 2 EI. Okay. So the final expression for RB will become, the final expression of RB is RB equal to W times 1 by 2 EA minus 1 by 2 kappa GA minus A square upon 2 EI upon 3 pi. Sorry, I think there is a less space here, so I just copy it from here and paste it in the next page. 3 pi upon 4 EA plus 3 pi upon 4 kappa GA plus A square into 2 plus 9 pi by 4. So this is the final expression for RB. Okay. So we have two question that asked here. So the first part is the vertical deflection of point B under the action of load W. Still we have to find this. The horizontal reaction force at B. So we have found the value of horizontal reaction force, and the next part is the vertical deflection at point B under the action of load W. So the vertical reaction, vertical displacement is given by taking the energy derivative with respect to the vertical load, that is W, using the Castigliano theorem. So we will be using this equation, that is we take the derivative of energy, total energy, with respect to the vertical load W. Using that, we will get the value of deflection, vertical deflection at point P. So vertical deflection at point B, vertical deflection at point B is given by delta B equal to del E upon del W. So if we take the derivative of total energy with respect to W, we will get integral over 0 to 3 pi by 2 f theta upon EA del f theta upon del W plus V theta upon kappa GA into del W plus m theta upon EI del m theta upon del W times A d theta, which is equal to integral over 0 से 3 pi by 2 RB cos theta minus W sin theta upon EA minus sin theta plus RB sin theta plus W cos theta upon kappa GA into cos theta plus MB minus WA sin theta minus RB A into 1 minus cos theta upon EI into A sin theta A d theta. Here, because we have taken the derivative here, so we put the dummy moment and forces be 0. So here MB turn out to be 0, and we already found the value of RB. So simply put the value of RB here, and we will find the value of, and take the derivative with respect to theta. We will find out the value of vertical deflection at point P. So using that, we can find out the vertical deflection at point P. So it's a very lengthy expression, that's why I'm not solving here. So you can solve it your own. I completely tell the procedure, how you derive and how you solve this question, and how you come to the final deflection equation at point P. So basically you just simply do the mathematics and you get the desired result. So this is all about question number 2. Now let's move to the next question, that is problem number 3. problem 3. Yeah. So this question says, for the structure shown, what is the deflection at end A? What is the deflection at end A? So I will draw the figure later. First I will write the question complete. At end A. Also determine the ratio of L to R if the horizontal and vertical deflection deflections of the loaded area A of the loaded end A are equal. P is the only force acting here. P is the only force acting here. P is the only force acting here. Okay, so the figure I'm drawing the figure right now. So you can also draw with me. So this is the figure for this question. So I'm repeating the question. For the structure shown, so this is the structure actually shown in this question here. What is the deflection at end A? So actually this is point A. So we have to find the deflection at this point. Also determine the ratio of L to R. That means the ratio of big L to small r if the horizontal and vertical deflection of the loaded end A are equal. That means the vertical and horizontal deflection at the end A is equal. So we have to find the ratio of small r to big L to small r. P is the only force acting here. P is the external load that is acting downward here. So coming to the solution part. So here also we will bifurcate this problem. That is, we will distribute the problem into two parts. The first is the curve part and the second is the straight part. So let's do that. So this is a curve part, left hand right hand part. So here is a curve. There is a load acting downward, which is P. Here we are assuming that because there is only a vertical load acting, so and there is no corresponding horizontal displacement here, only there is a vertical displacement, so we are assuming here a dummy force F, which is equal to 0. This is the center of the beam. Suppose this is making an angle of theta. So, and there is a shear force acting V theta. There is some extension force, stretching force F theta is acting, and there is some moment M theta. Now coming to the lower part, that is the straight part. So this is angle theta equal to pi. This is small r and this is P, load P, and this is the force F, which is equal to 0. Here there is V theta is acting, some moment acting, MB, and there is some force acting at theta, that is F theta. Now again here is some shear force. There is some compressive force F theta is acting, and there is also some moment. M theta is acting. Again there is some moment, M theta is acting. There is some compressive force Fx, and there is some shear force V theta, Vx is acting, which is at a distance of x. So here we have to find the first, we have two part. So first we have to find the vertical deflection at end A, and then we have to find the horizontal and vertical deflection of the loaded end A. No, sorry, vertical and horizontal deflection. We have to find the ratio of small big L to small r, so such that the horizontal and vertical deflections are equal. So here we are assumptions. We do one assumption here that we are neglecting the energy due to stretching and shearing, and only focus on energy due to bending. Here we are neglecting energy due to shearing and stretching. Shearing and stretching. And only focus on the energy due to bending. And only focus on energy due to bending. Okay, so here we are neglecting the energy due to shearing and stretching, and only we are focusing here the energy due to bending. So from now on we are only consider the energy due to bending in all these problem. So let's start with bending moment at any section of the curved surface. So bending moment at any section on the curved surface. On the curved surface, which is equal to summation over MO equal to 0, and on the curved surface it is given by minus of m theta. If you are considering this as a positive direction, so it becomes minus of m theta minus of PR. If you see in the figure, minus of PR, this is R and this is R cos theta. So this become R into 1 minus cos theta, this distance, minus P into R into 1 minus cos theta minus PR into 1 minus cos theta plus FR sin theta equal to 0. So from here we find the value of m theta, which is equal to minus of PR 1 minus cos theta plus FR sin theta. Okay. Now bending moment at this section, that is the straight section. So bending moment at any section on the straight portion will be given by bending moment at any section on the straight portion. So it is given by summation over m naught, where we are taking this direction as positive, equal to 0. So here mx minus m theta at theta equal to pi, because if you see here that here m theta is theta equal to pi. I hope I am audible to everyone. So yeah, this is m theta at theta equal to pi, because there you can see that the straight portion is at theta equal to pi. From here, from this point, then m theta, you can see the straight portion will lie at theta equal to pi. So therefore I am writing at theta equal to m theta at theta equal to pi plus v theta at theta equal to pi into x equal to 0. It is given by mx equal to, now we are already find the value of m theta in terms of theta, so it will become mx equal to minus 2pr minus fx. We are putting the value of cos theta, you can see here, after putting the value of m theta equal to m theta at theta equal to pi, so cos theta, that is cos pi, is minus 1 minus 1 minus 1 become 2, and it become plus fr sin theta, and sin pi is pi is 0, so it becomes 0 plus vx v theta x v theta at theta equal to pi is f. or minus F into X. Now the energy is given by integral over 0 to pi, because we have only semicircle, the curved portion is only a semicircle, that's why I am taking the integration over 0 to pi only, and then from 0 to L. So we have a straight beam. If we break the beam into two parts, then we have a curved beam of semicircular type, so we are taking integration over 0 to pi, and then after that we take integration over 0 to L. So 0 to pi minus PR into 1 minus cos theta plus FR sin theta whole square upon 2 EI into R d theta plus integral over 0 to L minus 2 PR minus FR square upon 2 EI into dx. Now here the question is to find the deflection, that is the displacement. If horizontal and vertical displacement at end are equal, then find the ratio of big R to small r. So for that we have to find the deflection at both horizontal and vertical, and for that we need to take the derivative of total energy with respect to horizontal force and the vertical force. So first we are taking the partial derivative of energy with respect to vertical force, so to find the vertical deflection. So here the vertical force is P, so therefore to obtain vertical deflection delta V del E by del P at F equal to 0 given by 0 to pi minus of PR into 1 minus cos theta. If we take the integration of energy, we will get this one plus Fx sin theta upon EI minus of R into 1 minus cos theta R d theta plus, now taking the derivative of second term, so it will become 0 to L minus of 2 PR minus of FR upon EI minus of 2R into dx. Okay, now again we are taking out the constant term outside of the integration, so it will become PR cube upon EI integral over 0 to pi 1 minus cos theta whole square into d theta plus 4p r square L 4p r square L upon EI. Okay, now taking the derivative, sorry, taking the integration of this term, so we will get 1 minus cos theta is 1 minus cos theta is 1 minus cos theta whole square, so it becomes integral of 0 to pi 1 plus cos square theta minus 2 cos theta into d theta plus 4p r square L upon EI, and cos 2 theta is cos square theta is 1 plus cos 2 theta upon 2. So using this we will get PR cube EI becomes 3 theta by 2 minus 2 sine theta plus 1 by 4 sine 2 theta 0 to pi by 2 0 to pi plus 4 p r square L upon EI. Now after calculating this value, we will get 3 pi p r cube upon 2 EI plus 4 p r square L upon EI, which finally become p r square upon EI 3 pi r upon 2 plus 4L. So this is the final expression for del E upon del P, that is the vertical deflection at point P. So here we are taking f equal to 0 because f is considered to be 0 here. There is no dummy force. We are forcefully at this dummy force, so we have to take it 0. Now we have to find out the vertical deflection. We have found the value of vertical deflection. Now we have to find out the value of the horizontal deflection. So now to obtain horizontal deflection, that is delta H, we have to take the derivative of total energy with respect to vertical force, horizontal force, which we forcefully assume at point B, because we have to find the horizontal deflection also, and for that we have applied a dummy force, that is F. So we have to take the derivative of total energy with respect to F, and after taking the derivative we will put the value of F to be 0. So it is given by integral over 0 to pi minus PR into 1 minus cos theta plus FR into sin theta upon EI into R sin theta into R d theta plus integral over 0 to L minus 2 PR minus Fx upon EI minus x dx. Now we have taken the derivative of energy with respect to F. Now we will put the value of F to be 0. So this will cancel out. This will cancel out. Okay. Now del E by del F will become, so actually this is the value of vertical deflection, PR square upon EI 3 pi R upon 2 plus 4L. Now del E by del F at F equal to 0 is given by minus PR cube upon EI integral over 0 to pi 1 minus cos theta sin theta d theta plus 2 PR upon EI integral over 0 to L x dx minus PR cube upon EI cos square theta upon 2 minus cos theta, because here we have you sin theta, then sin theta minus sin theta into cos theta. So that's why I'm taking sin theta into cos theta by 2 is 2 sin theta, sorry, sin 2 theta, but that is 2 sin theta cos theta is sin 2 theta, and therefore we take the derivative in this way, 0 to pi plus 2 PR upon EI x square by 2 0 to L. Now after solving this, we will get minus 2p r cube upon EI plus 2p r L square upon EI 2p r square r L square upon EI equal to PR upon EI minus 2r square plus 2L square. Okay, so this is the final expression for the vertical deflection. Sorry, horizontal deflection. Vertical deflection, we already found the expression of that. So this is the expression for horizontal deflection and this is the expression for vertical deflection. Okay. Now the question says, if the vertical and horizontal deflections are equal, then find the ratio of big L to small r. So we are equating those two values, that is delta V and delta H. So equating delta V and delta H, we will get PR square upon EI 3 pi r upon 2 plus 4L PR upon EI minus 2r square upon 2L square. L square minus 4LR minus r square 3 pi by 2 plus dividing this expression by r square, small r square, dividing the above expression by r square and putting L by r equal to rho, we get rho square. So it becomes L by r square whole square minus 4LR upon r square minus 3 pi by 2 plus 2 equal to 0. So it becomes rho square minus r cancel out, so minus 4 rho minus 3 pi by 2 plus 2 equal to 0. Now this is a quadratic equation, so we already know how to find the root of this quadratic equation. So on solving above quadratic equation, we will get rho equal to 4 plus minus under root over 16 plus 4 3 pi by 2 plus 2 by 2, because this ratio, that is the ratio of big L to small r, is not so yeah, because the ratio, that is big L to small r, are both the distance, actually the displacement thing, and therefore it can't be a negative value. So we are neglecting the rho, that is the ratio big L to small r value, can't be negative. Therefore, we are only taking the positive value. So the final ratio value, that is big L to small r, so big L to small r will be given by 4, 2 plus minus, sorry, we are already neglecting the negative value, 2 plus 16. So if we take 4 common in the from the root, so it will become 4 plus 3 pi by 2, 2. So it will become 4 plus 2, that is 6 plus 3 pi by 2. Okay, so this is all about question number 3. So I hope you all understand this problem. So yeah, today we have solved very good questions, which is based on energy method, on how to find the deflection and slope of the beam under various kind of deformation. So we have solved 3 questions. So starting with the session, I have briefly explained you some concepts related to energy methods, in which Cauchy-Gilliano theorem is one of them, and the Maxwell-Betty-Rayleigh reciprocal theorem was also one of them. And based on these theorems, we have solved some good questions, which is question number 1, 2, and 3. So this is all about today's session. I hope you really enjoyed this session and you understand it very, very well. It will be better if you come here after taking the lectures. So in that way, it will be clearly understood. So yes, so this is all about today's session. Thanks for joining today, and I will be conducting the last week session on the coming Friday, which is to be scheduled on 13th of October. Okay, so this will be the last week session, that is week 12 session, and in that session I will be discussing on the topic theory of failures. Okay, so this is the last session, this will be the last session, of course, and later on after that lecture I will conduct one session of only 1 hour, which is basically brief all the lecture, brief the overall, I will give you the overall briefing of the entire course, so that it will be useful to uh, recapitulate all the theory and numerical part, so that you will be do better in the upcoming exam of this NPTEL course. So thanks for joining today. Now you can leave the meeting. Bye.